Hi everyone, this is Sam Ganzfried. I'll be presenting on safe equilibrium. So I'm going to start with a motivating example. And so here we have the row player can choose actions C or D, the column player can choose actions A or B. Now we can see for the row player, if they choose C, they're going to get 9, a payoff of 9 regardless. If they choose D, they could get 9.01 if the column player chooses A, but they would get a really bad score, -1 million, if the column player chooses B. And now looking at the column player, actually choosing action B is strictly dominated. They always get 1.99 with B and 2 with A. So the column player, according to domination and game theory, would choose A, and then the row player would choose D. And so the unique solution according to dominance and also the unique Nash equilibrium solution is going to be here. The row player choosing D and the column player choosing A. Now we can see this is kind of problematic because if there's any chance that the column player is choosing B here, right, maybe they don't know that the payoffs are exactly 2 and 1.99, or maybe they're irrational, or maybe they have something else going on in their head, they want to hurt us or something that's not modeled in the game. If you have any doubt about it, you should play C, right? Because you're guaranteed 9. Here you might gain 0.01, but you might go to -1 million. And even more extreme if we're lives are at stake and really this is -1 billion or something way larger. And so we can see here from this example that Nash equilibrium and even dominated strategies are sort of not very robust to relaxing the assumption that the opponent might be irrational, even with some very small probability. And so this is going to be sort of inspiring, the motivation inspiring the work. I'll also present several other perhaps more realistic examples than this one. Many, like I just sort of described, many classic solution concepts in game theory assume that all players are rational and a common knowledge of rationality, etc. The most prominent being Nash equilibrium. Another concept, a maxi-min strategy, has the largest worst case expected payoff. And so this limits the potential downside against a really worst case situation. But often it's going to cause us to be very conservative and achieve a pretty low payoff. For example, you can think in a self-driving car, if we're always afraid of the worst possible thing happening, we might just not go anywhere, right? And so in two-player zero-sum games, this distinction doesn't really matter. These are equivalent. But for other games, multiplayer and non-zero-sum, they're not. And so in general, we can potentially obtain a very low payoff, like we just saw by following Nash equilibrium. But we can also get a low payoff by being too conservative with a maximum strategy. So neither of these is completely compelling on its own. And so we're going to propose a new concept called safe equilibrium that balances between these two. And so we're going to define an epsilon safe equilibrium as a strategy profile where each player is playing a strategy, player I is playing a strategy that minimizes the performance of the opponent with probability epsilon I, and is playing a best response to the opponent's strategy with probability 1 minus epsilon I. And so here, the epsilon represents the belief, the probability of being irrational. So with probability 1 minus epsilon, the player is rational and playing a best response. With probability epsilon I, they're irrational. Now, if we know how to model their irrationality, if we have some historical data or some other prior information, we can come up with a better model on how the opponent is behaving irrationally. However, in the absence of that, often we do not have any data, and so we're going to make the sort of safer worst case assumption that they're doing the irrational behavior that's worst for us. Now, our general goal here, there are some different goals that people study in game theory. Our goal is that we're a player, we're going to say we're player 1, and we want to come up with our strategy for playing the game. And so that's the goal throughout this work. And so with that goal in mind, we often would maybe want to set epsilon 1 to be 0 because we are rational and assume irrationality just for player 2, though our model is general enough that epsilon 1 does not have to be 0. And we're going to generalize this, as we'll see, to n players by assuming that we, player 1, are rational. The other players are all irrational with probability epsilon I, and playing a best response with probability 1 minus epsilon I, and with probability epsilon I, they're still irrational in the way that is worst for us, without any additional data to support a different model. And so let me briefly discuss a relationship to some other solution concepts that relate to sort of robustness. The most prominent being trembling hand perfect equilibrium, which is a refinement of Nash equilibrium that is robust to the possibility that players play each pure strategy with arbitrarily small probability by trembling. The formal definition, essentially, it looks at the limit as epsilon goes to 0, assuming that the players have to play all pure strategies with probability epsilon, and it's a limit point of equilibrium of these perturbed games. And so there's a big difference between looking at limit as epsilon goes to 0 and having epsilon be 0.01, 0.02, even 0.0001. And so, for example, in the initial example we saw, the unique Nash equilibrium was undesirable, and that's also going to be the unique trembling hand perfect equilibrium. But that doesn't allow for these epsilon to be, some constant value. And I'll also point out a distinction. While this is a refinement of Nash equilibrium, epsilon safe equilibrium is incomparable with Nash. Neither of them are subsets of each other. A second solution concept is a safe strategy, which is defined just for two-player zero-sum games. So if we let V star be the value of the game, then Nash equilibria guarantee at least V star an expectation. A strategy is epsilon safe if it has a worst case expected payoff at least V star minus epsilon. So for epsilon equals 0, it would be Nash equilibrium. Now this is just two-player zero-sum games. Well, our solution concepts are motivated by non-zero sum and multiplayer games. So this is basically just more formal notation for what I just described. For a two-player game, we have it's epsilon safe equilibrium. We have tau star and rho star, where rho is going to be the best response and tau star is going to be worst case for us, and so there's probably epsilon on the tau and 1 minus epsilon on the rho. And this is basically what I just said. And so let me talk about existence. So the first thing we'd like to know is for a given epsilon 1 and epsilon 2, is it guaranteed that there exists an epsilon safe equilibrium? And it turns out the answer is yes. It is. I'm not going to go too into proofs in this talk. They're in the paper, but we can see this by constructing a 4-player game that's equivalent to this epsilon safe equilibrium. And so since Nash equilibrium implies that the 4-player game has an equilibrium, that's going to correspond to an epsilon safe equilibrium. Now, for the computation complexity, you may be a little bit unsure. On the one hand, a maxi-min strategy can be computed in polynomial time. A Nash equilibrium is p-pat hard, and so this is maybe somewhere in the middle. It's unclear. It turns out that for a two-player game, that it's p-pat hard to compute an epsilon safe equilibrium. And so this is a sketch of the proof. The full proof is in the paper. I'm not going to go through it. But the point is that both the existence and computational properties of safe equilibrium are the same as for Nash equilibrium, though I point out that it's not a refinement of Nash equilibrium, it's a distinct, incomparable concept. Now for n-player games, I discussed it before, player 1 is sort of the special player. For the other players, they're going to have the tau star, which is the worst case for us, the rho star, which is their best response. And player 1 is just best responding, which is ourselves. And so we also have similar existence and complexity results for the n-player formulation. So now here's an example, the game of chicken you might be familiar with, where two players can either swerve or go straight. Turns out there's a unique mixed strategy Nash equilibrium where each player swerves with probability 0.9. There's also two pure strategy equilibria where one swerves, the other doesn't. The unique maxi-min strategy is to always swerve with probability 1. Now, if we set epsilon 1 to 0, so that we're rational, it turns out that for epsilon 2 between 0 and 0.1, that our mixed Nash is epsilon safe. And for epsilon 2 between 0.1 and 1, that the maxi-min is epsilon safe. However, it's not, epsilon safe does not need to be one or the other. If we, for example, set epsilon 1 to be 0.05 and epsilon 2 to be 0.15, epsilon safe is for player 1 to swerve with probability 0.95 and player 2 to swerve with probability 0, which isn't a Nash or maxi-min. Another example here, we have a security game where the row player is choosing a target to defend and the column player is choosing a target to attack. And so a Nash equilibrium is for the row player to choose, these probabilities, 0.31, 0.46, 0.22, and a maxi-min is to choose these other probabilities, 0.61, 0.01, 0.37. If we set epsilon equal to 0, epsilon 1 equal to 0, it turns out the Nash is epsilon safe for the range epsilon 2 between 0 and 0.314. The maxi-min is epsilon safe for the interval 0.569 to 1, and for this intermediate range, this other strategy, 0.44, 0.36, 0.18, is epsilon safe. So I'm not going to get too into what we should choose for the epsilons, but we can see one important thing that can help justify a solution is to look at the intervals and see if one strategy is an epsilon safe equilibrium for a big interval of the epsilons if we're unsure, which value we want to go with. So I'm going to talk about exact and approximation algorithms. I'm not going to get too into it because they are extensions of Nash equilibrium algorithms, some of which I've worked on before, some of them based on fictitious play. So for two-player, there's a mixed integer feasibility program modification that modified version of a Nash equilibrium algorithm. And similarly for three-player, I worked on this, which is the fastest complete algorithm based on a quadratic mixed integer feasibility program. And so we also have approximation algorithms, which are kind of like fictitious play, where we're doing fictitious play both over the tau and the rho, both for two and n players. I'm not going to get too into the details, but I'm going to talk about the running time. So first, we're going to use sort of standard values. Epsilon 1 is 0, epsilon 2 is 0.05. We can see the scalability of the exact algorithm. It's a fraction of a second up until you get to 25 pure strategies, then it starts to take a few seconds. For n players, now this is harder problem, and it's pretty common to have poor scalability for n players. But anyway, it takes a few seconds, and then once you get up to n equals 5, it takes longer. And for the approximation algorithm, it's much faster. We can see that we can get up to 25 in a fraction of a second, but it has some degree of approximation error. I also used a version of fictitious play that has maxi-min initialization, which is a little bit slower. We can see for 25 it takes about 1 second, but it has much lower approximation error. And so, this is a very valuable, scalable approximation algorithm. For n players, we can also do approximation algorithms. I'm going to do epsilon 1 is 0 and the others are 0.05. We can see that, a fraction of a second up to about a second for 25, with a sizable approximation error. And if we use 10 initial strategy profiles with maxi-min initialization, we can reduce the error by about half. And so, it takes on the order of seconds and has a pretty low approximation error. And so you can see that there are both exact and scalable algorithms that are practical for computation. So to conclude, we presented this new concept, epsilon safe equilibrium, in which players are potentially arbitrarily irrational with probability epsilon I. We proved theoretically that it's guaranteed to always exist, and its computation is p-pad hard. Both of these properties similar to Nash equilibrium. We devised exact and scalable approximation algorithms for both 2 and n players. I expect this analysis and the algorithms should extend straightforwardly to imperfect information, extensive form games, stochastic games, other settings, although we need to explore that in future work. I also want to point out, if we have historical data, we don't need to have the model of irrationality be the worst case for us. That's just sort of a pessimistic model without any additional information. If we have an opponent model or a prior or other data, we can incorporate that to have a better model of irrationality. Now, as we know, game theory is being applied to a lot of high-stakes situations like national security, self-driving cars. And it's essential that the strategies are able to accommodate the possibility of opponents' irrationality. We can't simply just make a matrix, plug it into an equilibrium solver, as we saw in the initial example, without accounting for possibilities of irrationality, or we risk these very low payoff situations. And safe equilibrium effectively balances between rationality and safety, creating strategies that are robust to arbitrary degrees of opponents' irrationality.